the purpose of the greenhouse gases is that they trap a percentage of the thermal radiation that's emitted from the Earth's surface, and they give us a benefit of closing the range of temperature on the high and low side that we'd otherwise be getting if we didn't have them in the atmosphere. So when we talk about these greenhouse gases, we have to take a look at radiation. And what is radiation? Radiation is a amount of energy that can be transmitted through a medium without anything in the medium itself. Unlike sound waves, it can travel through the atmosphere, but can also travel through space without a medium. And it comes in all shapes and sizes. Just to give a brief overview of how the radiation spectrum works, at the top we have the really dangerous radiation, the cosmic ray photons, the gamma rays, and X-rays. This is all nuclear stuff that comes from the sun and nuclear reactions, very harmful to human life. But our atmosphere screens all of this radiation out. That's part of the solar wind and other things going on in space. We have to get down to the ultraviolet range before we see any effect at the Earth's surface. And the ultraviolet radiation, in case you didn't know it, is the kind that will burn your skin if you've been out in the sun too long without sunscreen.
Okay.
And just below ultraviolet is visible light. Now that's the radiation that your eyes are sensitive to so that you can see. And if we go just below the visible light, we get into this infrared stuff. And that's what we're really talking about looking at when we look at the greenhouse gases. If I struck a match in a dark room and blew it out, and you looked at that match, the last color you'd see before you didn't see anything is the color red. So we call it infrared because the next wavelength lower than that the human eye can't perceive is infrared radiation.
Okay.
And that's thermal radiation. It's heat energy. And this is the part that the greenhouse gases emit and absorb. And we go down from there into microwaves, radar, television, shortwave radio. The real low energy stuff is at the bottom. So the shorter the wavelength and the higher the frequency, the more energy is available. And the longer the wavelength and lower frequency, the less. Infrared lies right into here, and that's what we'll take a look at in our next graphic. So let's focus on that part of the spectrum and take a look at these greenhouse gases and where they're absorbing and emitting their energy. At the bottom here is microns, and this is just basically a close-up of the last graphic I showed you, starting at around 6 microns and going out to 14. And take a look at where these greenhouse gases absorb their energy. Carbon dioxide is up here near the 15 micron wavelength, and then we've got one at ozone around 10. But look at where water vapor is. Water vapor starts around 8 and goes down to 5. But look at the area. It's significantly larger than CO2. But the important thing is, just like I told you, it is absorbing its energy at a much longer wavelength. That means it's got much less energy than water vapor. Water vapor does all the heavy lifting in the atmosphere as far as absorbing and emitting these the radiation.
Are we discussing clouds in layman's terms? We don't get too scientific.
No,
here.
we're not. The clouds are even more of an absorber of radiation because they don't selectively absorb it. They absorb at all the wave bands. These are just partial absorptions that are occurring around 7, and then you got another one with CO2 up around 15. But the important thing to get out of this graphic is CO2's energy is very weak compared to all the other greenhouse gases. It absorbs very little of the radiation and it emits very little. So let's take a look at some temperature graphs if we plotted these, just to give you an idea of what I'm talking about with this. There's 3 temperature plots on this graph, and it's not important to understand all the physical concepts of it. On the left, we could just say that's watts per square meter. On the right, we compare that against wavelength, and then we draw the temperatures. The 300-degree temperature is absolute, so that's about 70 degrees. It would be the area underneath that line right here that goes all the way to the edge and back to the other edge is the total energy in watts per square meter that the 70-degree temperature would radiate away. It's a little over 400 watts. And then we draw an intermediate line which would represent something the atmosphere would absorb and emit, and that's 250 K, around minus 20 centigrade. And the area underneath that curve is what it would absorb and emit. And the last one is more representative of CO2's radiation. It's 200 degrees Kelvin, actually a little bit less than that, and it only is 78 watts per square meter compared to the surface's 400. So if you look at the hierarchy of the curves, the important thing to get out of this is that the area underneath this 200 line is part of the area of the 250 line. And so what that tells us is there's no place for carbon dioxide to store itself up in the atmosphere. What's emitted will be what's
And
absorbed,
a
a little
little
bit more gets radiated away from the CO2 because the atmosphere is warmer than the CO2 temperature. So it absorbs all of the CO2, emits it all away, plus an additional amount because the atmosphere is warmer than the CO2 radiation is. So the real purpose of these greenhouse gases and the carbon dioxide is not to cause anything to build up in the way of heat. What it does is it radiates it away plus more. So at night we get the benefit of this by having at night we get the benefit of having the radiation absorb at the ground, and then it keeps the nighttime temperature a bit higher, but during the daytime it's actually cooled the atmosphere. So when the sun comes back around and starts heating up the earth again and mixing those gases, the trade-off is on the high temperature end there's also a loss, just in spite of the fact you've had a gain at the low temperature loss during the nighttime. So we get a benefit from these. It doesn't cause warming. It narrows the length of the temperature span we would otherwise have in day and nighttime another graphic that illustrates that very well. Another reason why it's like a zero-sum gain if you talk about the radiation from carbon dioxide. The Earth radiates in one direction towards space, and then those greenhouse gases, water vapor and CO2, absorb their percentage of that radiation. But the atmosphere radiates it in two directions, back to the surface and also to outer space. So we get roughly half of that back. And so for whatever's emitted out to space, we get half back, but there'll be an equal amount radiated away to space. So what we get back from the atmosphere also radiates an equal amount to space. So you get the benefit of reduced cooling at the surface, which is not warming, by the way, at night, and then during the daytime, because this process in the atmosphere actually cooled it, we get a slight reduction, a similar reduction in daytime temperature versus the raised nighttime temperature by the absorption and the emission process. Now the other side says, they only look at the warm side. They basically tell us that, if you increase CO2 in concentration, you'll absorb more energy out of it. That's true, you'll absorb more out of it, but like I said, the atmosphere will emit an equal amount as well. So what you get back at the surface, you're losing from the atmosphere. It has a minimal effect in causing any warmth. The thing that's really sad about this is they are relying on these models, which we know are not accurate. We know they're full of flaws. We don't have time to go into to all of them tonight and why they are.
Hasn't pretty much everything in the Al Gore's movie been debunked?
Pretty much everything has. Al Gore's movie is a disaster. It's not accurate. The portrayals of how everything works, the way he describes it, is wrong. It's just stunningly wrong.
You do know he flunked out of divinity school.
Well, that doesn't surprise me. There was a big climate conference in New York last March about this, and this is actually comparing what the global climate models predicted and what we've actually observed in the north and southern hemisphere. The left-hand side is what we would call the fingerprint of the global climate model. Across the bottom of this graph is latitude, so the middle of it is the equator. The right side is going to the southern hemisphere, and the left side is approaching the north hemisphere, north pole. And then the vertical axis is altitude, so we're at the surface, and the top is up to a height of 10 millibars, over 28
so
kilometers
Panama
high.
is like right here.
Yeah, it's down close to the equator.
Okay.
And this is what the global climate models predicted worldwide would happen with the temperature in the atmosphere based upon doubling CO2. And this is the change in temperature they predicted from 1958 to 1999. There is a huge bubble, as you can see, of a warm anomaly over the equator and the tropical areas that's over a degree. In fact, it's like 1.2 degrees. They predicted a very large warming, which is a very important theoretical test for them to have passed to show the validity of their models. And if you take a look at the right-hand side, by radiosonde observations, where we keep track of the upper atmosphere every single day, we took the same time periods and we constructed what's actually happened with the same scaling to the Earth's troposphere. And the center is the equator, and then we're going to the north to the left, and we're going to the south to the right, and then the vertical is height up to 28 kilometers. Does the right and left-hand side even remotely resemble? And a very slight warming away from the equator in the lower part of the troposphere. And that is the exact opposite of the fingerprint of the global climate model, because their warming is concentrated at an altitude of about 12 kilometers above the ground. So there's a huge difference in what the models predicted and what we've actually observed.